Well, thanks for the invitation. I'll just then start. Well, I do see that there are people actually in person. Hopefully in the future I'll be invited once more. And then I can actually be there in person as well. So today I'm going to talk a bit about the fuchsia learning, and then in particular fuchsia learning with a large-scale language model. As you have perhaps seen, the whole hype around the GPT-3, and then trying to dissect what GPT-3 can really do in terms of the fuchsia learning for us. So first, we need to talk a bit about what we mean by fuchsia learning. At least, I'm going to talk about what I thought fuchsia learning meant. So fuchsia learner is a very interesting thing. So it's a machine learning algorithm that is going to take as the input not just a single example, but it's going to take as the set of examples, of course, set of few examples, and then try to output a model. So it's going to be a model, or in this particular case, we're going to say that it's going to output the parameter configuration of a machine learning model that is now able to handle, for instance, classify a new example based on those few examples. Now, of course, this fuchsia learner is not a magic box. It also has its own hyperparameter. Let's use phi to denote them. And then given that hyperparameter, you can imagine that this fuchsia learner is a function that's going to map a small number of examples into the parameters of this machine learning model G that's going to be able to classify a new example X prime. And then this kind of fuchsia learning has a very long history, but if I look at just two representative examples from the recent years, one is a prototypical network from Snell et al. From 2017. In this prototypical network, what prototypical network does is to learn how to embed a new set of examples into a few vectors, so-called prototypical vectors that corresponds to class vectors. And then given a new example X prime, what it does is to simply compute the dot product between this one of the prototype vectors and then this X prime, or the embedding of the X prime, in order to see how close this X prime or the embedding of X prime is to one of the prototype vectors. And then the closest one is going to be selected as the class to which X prime belongs. So this is kind of one of the prototypical example of the fuchsia learner from the recent years. Another example is the model agnostic meta learning, or MAML, by Finel from 2018. So in this case, MAML is going to output not the not the embedder itself, but it's going to output the initialization of the parameters for the final neural network G that can be tuned using SGD with a very small number of examples, x1 to xn. So I'm going to use the capital N to denote the number of examples. And then once the initialization is given by the MAML, we simply use a off-the-shelf stochastic gradient descent or just gradient descent algorithm, starting from the initialization that was computed by the MAML using a small number of examples. And then the final parameters are going to be used by us to design a neural net that's going to classify a new example X prime. So all these things are really interesting idea. But one thing you notice here is that the fuchsia learning in this particular perspective is really nothing but supervised learner. It's just a supervised learning where each example corresponds to a set of examples. So we now have a training set of fuchsia training sets. We have the validation set of the fuchsia sets. We have a test set of the fuchsia sets. And then now, just like any other supervised learner that we use, we have parameters, phi, and then also the hyperparameter. So you can imagine that this is a hyperparameters, let's say the lambda there. And then the result of this supervised learning is going to be the model. So the regression model itself, that is f of phi, that's going to take as the input one of the sets, or the new set, that is a set of few examples, and then outputs another model that's going to be used to classify a new example based on this small number of examples. And then just like in any other supervised learning, we can solve it by training, that is to minimize the loss function over the training fuchsia sets. And then we can also choose to do the model selection or the validation using, again, a set of validation fuchsia data sets. And then at the end of the day, we are going to report how well this fuchsia learner is going to work by reporting the accuracy on the test fuchsia or the set of test fuchsia sets. It's a bit confusing, but as long as we make a connection that the data sets correspond to examples, the fuchsia learning or the meta learning is really nothing but a supervised learning or unsupervised learning, depending on what we want to solve. So what this means is that even in fuchsia learning setup, we have to run model selection. And then that's actually makes it very complicated, because collecting one data set is hard enough for us, because we all know that collecting data, cleaning them up, and then post-processing them, pre-processing or the post-processing them is really difficult. But now we need to build a data set of data sets. And then this is just inevitable because of the free parameter feed, the hyperparameter that we need to choose. That hyperparameter is a parameter of the fuchsia learner. And this happens not only in fuchsia learning, but also in transfer learning, multilingual learning, multitask learning, and whatever the problems that we have, where we have more than one task, we need to have training tasks or the training data sets, validation sets, and also the test tasks as well. And then this actually gives us a slightly different view into how we look at these prototypical networks or the MAMO, the earlier work, is that there's always a phase of the meta training plus the meta validation that is followed by the meta testing. And then we have to be, just like in supervised learning, we have to be very careful about how we split the data sets or the data sets of data sets between these stages. And the same for MAMO as well. So we need to have the metadata, meta training set and meta validation set. And then we also need the meta testing set. And then we cannot really go back and forth between these two. Otherwise, we're going to overestimate how well our fuchsia learners are going to work in the future. So it's really, really tricky. It's just difficult to collect all this data. And then we have to be super careful about the information leakage across training, validation, and test. And then we have now 2 stages of training, validation, and test. So in order to tackle this challenge, people have starting from 2018, build up a new benchmark for the fuchsia learning or the meta learning. But of course, there are only a few of them. We need to work really hard on trying to come up with a better benchmark so that we know whether we are making a progress in this kind of fuchsia learning or the transfer learning better going forward. Now, this is what I thought fuchsia learning was, and I believe a lot of people thought what fuchsia learning was. But last year at NeurIPS, OpenAI team got a best paper award by the paper titled Language Models of Fuchsia Learner. And in their abstract, let me just read it out. They said that we showed that scaling of language models greatly improves task agnostic fuchsia performance. GPT-3 is applied without any gradient updates or fine-tuning, with task and fuchsia demonstrations specified purely via text interaction with the model. So exciting. I'll tell you why it is so exciting. But let's just believe that this is extremely exciting. And then in their paper, the paper is actually quite dense, and then it is also long as well. And then they actually do talk about what they mean by fuchsia learning with language model. Let's forget about 0 shot and 1 shot. Let's look at the fuchsia on the right side of the slide. So what they do is that they're going to just make a text that's going to be given to the GPT-3, so that the GPT-3 is going to read about the problem and then solve for a new problem. So it's going to be task description written in just plain language, and then there will be a few examples. So in this particular case, it's going to be about translation, fuchsia translation. So the task description is going to be translate from English to French. And then some examples are going to be sea otter is Retrouvez. I guess my pronunciation is really horrible, but and then another example is going to be peppermint, go to menthe poivre, and then plush draft is to draft plushé, I guess, yes. And then we're going to ask the language model, now given these examples and then this task description, what should cheese be translated into in French? So it's actually extremely intuitive. It looks like we almost can solve any problem in this manner, because all we need to do is to use our knowledge of language to just write down the task description and then provide the examples. So what does it mean? Unlike a prototypical network or MAMO or those examples from the early days of the fuchsia learning, what GPT-3, according to OpenAI team, allows us to do is start with some example, these few examples. So we have x1 to xn, and then we have a new example, x prime, and then so-called prompt engineer is going to look at this problem carefully and then come up with the task description as well as the examples. So that's going to be called prefix. And then this prompt engineer is going to choose what are possible outputs, what are the possible answers, And then we simply send it to GPT-3 and then ask GPT-3 to tell us what should be the answer as the next set of tokens or the next sequences of tokens out of these possible target class tokens. And this is actually quite amusing. The fact that it just worked itself is quite amusing, and then the fact that this paper got best paper award turned out to be also amusing as well. And when you look at it more carefully, looking a bit beyond this excitement, you notice that there are a lot of hyperparameters. You have to decide on how to make the task description. We have to decide on what is the right way to present the examples. We have to decide on what is the right set of the target tokens from which GPT-3 should be able to choose the answer from. And then according to the paper, you often need to choose how many training examples to present in order to get the optimal performance out of it. So there are a lot of them. But then this is quite different from the conventional notion of future learning in the sense that there's no notion of the separate meta training nor meta validation future task. And then without this, you start wondering, at least I started to wonder, how do we choose these hyperparameters? That is, how do we know how to talk with GPT-3 so that GPT-3 is going to answer for solve a new problem in a way that I want it to do so. So if it's really purely via text interaction, I should be able to choose these hyperparameters using the text interaction as well, but it did not look like it was doing so. But regardless of whether I have that question or not, but this paper got the best paper award, and there has been like flurry of follow-up papers, and then those follow-up papers were getting all those best papers as well. And then what we did, so together with my PhD student Ethan Perez and my colleague Dao Kila from the Facebook AI research, we just started to ask around, how did they choose prompts? Prompt seems to be a very complicated thing to choose from. Now, how did they choose it? So we looked at the OpenAI's paper. They said that they experiment with a few values of K on the development set and then run the best value. So they said that they use the development set. But what does that mean? We're talking about the future learning. If we are assuming that we are given only a few labeled examples, where does the development set come from? And then we read another paper, let's say, for instance, Chin and Eisner 2021, which received the best short paper award from the NACO, that is the NLP conference, just a few weeks ago. They say that they use a gradient-based training, not the prompt engineering, but still, they say that they test with a model that performs best on the dev set. Where does this dev set or the validation set come from? If it's future learning, shouldn't we only work with the few labeled examples for the target task? And then we started to go into more and more paper because everyone is excited about GPT-3. So there are so many papers to just consult. It looks like almost everyone is using dev set or rely on the previous hyperparameters or the hyperparameters found by the previous authors who use the dev set, unfortunately. So what that means is that a lot of the future learning with GPT-3 has not really been a truly future learning in a sense that I've been thinking about, or a lot of the people in the community have thought about. Rather, it's been a somehow weird version of the future learning, where the future learner has not only access to a small number of the labeled examples for training, but also had access to quite a lot of labeled validation examples. Now then, at this point, it becomes a bit unclear what it means for future learning to be future learning. So what this means is that unlike what we thought was happening before, the prompt engineer was in fact looking not only at this small number of labeled examples, but also a very large number of the labeled validation examples in order to make GPT-3 work as a future learner. And let me just quickly, come back to the excitement part. I'm still excited about the whole thing, despite this kind of, let's say, potential flaw that we identified earlier, because the possibility of doing a future learning or even zero-shot learning with a language model is extremely exciting. And then, we already started to see this in 2014 or so when I was working in Montreal to make the first kind of, let's say, viable neural machine translation system. One of the kind of quick experiments back then we did with a very small model that we had was that let's try to translate the unknown Korea is a friend of the United States using our English to French translation system using a neural network. And then in the translation, in the output, we're going to prevent our model from generating unknown token. Then this model was in fact filling up this unknown part with the south. But when I replace a friend with the enemy, it actually replaced the unknown with the north. And then we were like, whoa, this is really cool. So the neural net is actually learning something about the world out of the data set we have thrown in to train this translation system. So this is, we didn't really realize the significances of this finding back then, but it's really exciting because this really allows us to interact with the neural net in a way that is very different from how we have been doing. That is that the curating data and then give the data to the model by designing a loss function, designing an optimization algorithm, and then trying to minimize it. So it is still exciting. So I just want to just re-emphasize that one. But unfortunately, it doesn't look like they were actually using only a few examples. So my student Ethan and I decided that, okay, let's try to test it. Let's see if we can really use GPT-3 when we are only given a few labeled examples. And then we're going to use those few labeled examples for both hyperparameter selection, that is a prompt engineering, as well as training, that is to give the engineered prompt together with the examples to the GPT-3. And then we're going to evaluate, so only test it on a large held out set, such as a test or the development set, but we're not going to use them for the hyperparameter tuning nor training, so that we really know what we can expect. Let me see, yes. So what do we need in order to run these experiments? So as usual, we need a Fuchsia learner, but the Fuchsia learner is really just GPT-3. So we're going to use the GPT-3 as it is, the large-scale pre-trained version accessible via API from OpenAI. Predictor is also GPT-3, or more so, it's a dot product. So we're going to use the provided API. What we now need is a hyperparameter selector. This hyperparameter selector is going to have the same labeled examples that are available to the Fuchsia learner as well. This hyperparameter selector, needs to choose the hyperparameter out of these few examples alone. So in one line, we have the dataset D that has only a very few examples. We're going to use that to choose the hyperparameter. So that's the H of D. And then using that hyperparameter, our Fuchsia learner, F is going to output the model or the parameters for the predictor G. So that's going to be F of H of D and D. And then given that one, now G is going to output some prediction of the new example X. And then we have the loss function L. And then we're going to test the loss, or we're going to compute the average and the variance of the loss over the test examples. So this is true Fuchsia learning in a sense that, as you can see, both the hyperparameter selector H as well as the Fuchsia learner F, both of these only have access to a few labeled examples, like truly few labeled examples. This is unlike many of the recent studies that have relied on GPT-3, where somehow the hyperparameter selector H had access not only to D, that is the Fuchsia dataset, training set, but also the D prime, which turned out to be much, much larger, also labeled, and are examples that comes from the same distribution from which the training set, Fuchsia examples were drawn. So what that means is that these almost Fuchsia learners have been generally optimistic in estimating how well GPT-3 works as a Fuchsia learning. So we really wanted to see what the gap was. So, how do we choose the hyperparameters when we have a very small number of examples? We just decided to try some of the many of the classical ways to do so, such as a k-fold cross-validation, where we often use k to be 1. So we're going n. So we're going to do the true cross-validation, or using the minimum description length, or we tried a few other things. But at the end of the day, all of these the choice of this kind of, let's say, prompt selection or the hyperparameter selection criteria turned out to not matter that much. So why is it difficult and why is it interesting? Because prompt engineering sounds really exciting because it feels very intuitive, and then it feels like, because of that intuitive nature of the natural language, it looks like it's easy to solve. But it's actually a very difficult problem because the space of the prompts is combinatorial. Prompt length vary from one to another, and then the placement of the examples can actually vary from one to another. We can always permute the examples as well. So it's really not easy to do any kind of optimization or search in this space. So even us, we couldn't actually do the full search over the prompt space, but we decided to rely on a set of predefined prompts from the earlier papers. What that means is that we are still going to overestimate how well the Fuchsia learner based on the GPT-3 works. So we're going to answer 3 questions. The first one is that when we don't use this D prime, that is a very large validation set, can we still identify a good prompt that we could have selected had we used a very large validation set? Second question is that can we actually do Fuchsia learning better by selecting the prompt using this cross-validation or the MDL criterion, then simply choosing one randomly selected prompt, simply using a one randomly selected prompt? This is a really kind of, let's say, dumb question, and then we should always do better than randomly selecting the hyperparameters, but because we have so few an example, it's not that easy. And then the third question we want to answer is that what is that gap that we talked about? So how optimistic has the community been just because of the excitement out of the GPT-3 paper? So I'll just go through it quickly. I still have about 7 minutes. So let's talk about the experimental setup quickly. So we focus a lot on the so-called llama dataset. This is a benchmark that was created and released in 2019 by Petroni et al. For testing the capability of retrieving facts from a language model. And then it has a bunch of these, the factoidal, let's say, question answering, let's say, examples that we can use in order to see if a given language model contains some knowledge about the world. And then, it's a pretty large data set, so we use a very particular split called T-Rex, and then we also use a very difficult examples only that were selected by the Porner et al. In last year. And then the prompts, Llama, this benchmark actually comes together with a manually curated set of prompts. And then last year, Jiang et al. In their paper, they actually designed the so-called Alpaca, where they created a way to automatically paraphrase all these prompts so as to improve the performance on this Llama data set. So we're going to use all those, let's say, highly curated set of prompts, and then we're going to use cross-validation, for instance, to choose the best prompt out of this. So we are still going to overestimate how well Fuchsia Learner based on GPT-3 does, but we believe this is still a good place to go. And that's the reason why we want to use the language model, right? So we can rely on our intuition and our way of using natural language to interact with this very large language model. So let's try to answer the first question. Can we actually identify the best prompt when we have a very few examples alone? It turned out that the answer is actually less than 30% of chance. So let's say best prompt is the prompt that we can choose by using a very large, like the 10,000 labeled examples as a validation set. But when we use only a very small number of labeled examples in a truly Fuchsia setting, like using 5 examples or up to 40 examples, we could only identify the best prompt less than 30% of the time. And then the unfortunate thing is that it was getting more and more difficult to identify the best prompt as the underlying language model got larger and larger. That's what you can see on the left side of the plot of the slide. And also increasing the number of examples from 5 up until 40 didn't change anything, unfortunately. What that means is that when we have a few labeled examples, it's just not possible for us to identify the good prompts, which is unsurprising. We have only 5 labeled examples based on which we should choose the prompts out of this combinatorial space. And even after the manual curation, we ended up with like 100 prompts that look all equally good. And then 5 examples are just not enough for us to get the signal out of it. Okay, so second question. So, so far a bit gloomy. Second question, can we do better than a randomly chosen prompt? So we're not going to look at whether there is a best prompt and whether we can choose it, but instead we're going to just look at the actual accuracy. And then we want to see if we can do better than selecting the prompts randomly. Turned out that barely so only. And then the variance is really, really high. So, and then forgetting about the variance, we could only get about 20% relative improvements over selecting the prompt at random. And then nearly 60% of time, the accuracy was lower than the average accuracy of choosing the prompts at random. And then that's not that great. So what that means is that if we wanted to deploy this kind of GPT-3 based fuchsia learner without any knowledge about the target task, then there's a big chance that the 60%, there is a high chance of, let's say, about 60% of time that the trying to do good at the prompt engineering is going to result in a worse performance than just randomly selecting any of the prompt. Now, some might say that well, that's good because that just means that we can choose a prompt randomly. But then, I would even say that well, that's not necessarily true because what is the random selection in this manually curated prompts means that somebody already curated based on the knowledge of the task before. So it's a bit of a confusing situation, yes. And then this is not only for this particular data set. We try with multiple data sets, we always end up with a very similar conclusion. And then in case is that we must have a way to choose a prompt somehow, a priori, with some other information, and cannot rely on these few examples alone. And then this is actually, this agrees well with our conventional definition of what we mean by fuchsia learning. So then, can we do, how much do we lose with the true fuchsia learning? So we want to look at that gap. How optimistic were people, during the past year and a half since the GPT-3 paper was published? By the way, it's not all too gloomy at this point. So there is a clear gap. So what we see is that if we use a very large validation set, yes, we can choose a much better prompt, and then there is always a significant gap in terms of the classification accuracy compared to how well we can do by using cross-validation on the very few examples alone. And then often, we do no better than choosing a random prompt. However, one good thing is that as the language model gets larger and larger, somehow we always get a better accuracy, regardless of how we choose prompts or the hyperparameters. What that means is that the larger the model, we actually do see that the language model knows more and more about the word and can answer the questions better than when the language model was much smaller. It's just that the larger model does not necessarily imply that we know how to ask this language model to answer these questions as well as it could. And then this is, of course, not only about prompt engineering. When we're trying to just fine-tune this model using some kind of optimization algorithm, those optimization algorithms tend to have some hyperparameters such as the learning rate or whatnot, and then tuning them turned out to be very difficult if we assume a true fuchsia learning setup. And then what we see is that however we tried, we always do worse, significantly worse than the best performance we can get if we had access to a large validation set. And then this best performance we get, that is the unrealistic scenario, is exactly what all the other papers have reported it turned out. So we, as in the field of natural language processing and machine learning, have indeed been a bit blinded by our own excitement, and then have been reporting optimistic accuracies on what we can do with the GPT-3 based fuchsia learning. So we've made some somber realizations. That is that the fuchsia learning is still challenging, very, very challenging with GPT-3 or even with the GPT-X, whatever the X may be, is going to be very challenging just because we have only a few examples. There's not enough signal to learn a new model. That was the original challenge of the fuchsia learning, but it turned out that there's not enough signal to find a good hyperparameter configuration, including prompt engineering, however well the language model was trained. In other words, we need something extra to find a good hyperparameter configuration. So in the case of the meta and transfer learning, as we talked about at the very beginning of my talk, we need many similar tasks that are available for us to do the meta learning or the meta hyperparameter tuning. Or perhaps the right way to view about it is that we need to look at the prompt engineering as an inference problem, and then try to solve it from the probabilistic perspective, and then trying to incorporate all this uncertainty there is in choosing the prompts. However, this seems like somehow trying to solve a simpler problem with a more difficult problem. So I'm not sure whether that is a right way to go about. However, I want to finish my talk by saying that it's still extremely exciting. That is that this idea of being able to do fuchsia learning with language models or a very well-trained large language model is extremely exciting, because this is one way that I see as one very promising way for us to bridge so-called symbolic structure or the symbolic instruction with the neural net-based learning. That is that the GPT-3 or this kind of language model that is large scale and then trained on all available data works as a neural execution engine. And then it can actually solve a lot of problems that we didn't even know how to code it up ourselves. But then we have this, and then this neural execution engine now can actually interact with us, not via the optimization algorithm, nor via only the data, both of which are the things that we have been using conventionally, but with the symbolic instruction. And then this is a very exciting and promising direction, in my opinion. And then what that means is that this actually allows us to look into many other developments in the field of machine learning, broader, let's say AI field, and then use all those developments into making these fuchsia learners better. So for instance, if we think about the example-based meta learning, now in this GPT-3-based fuchsia learner, this is essentially the program induction that we need to solve. And in the case of the description-based meta learning, it corresponds to program synthesis. So what have people been doing in the program induction and program synthesis? Can we actually learn some of the lessons from there in order to solve this problem of learning how to interact with just GPT-3 or the language model-based fuchsia learner? So perhaps this idea will truly withstand the test of time as it was described by the NeurIPS 2020 Best Paper Award Committee. And that actually does conclude my talk. Thank you very much for listening. And then let's see if there are some questions here. Thank you.